So I think we can start, and today is the first event for the seminar on the second trimester in random geometry and quantum gravity. And so today we are at IHES, and we thank them for the hospitality. Let me also thank our sponsor, the Fondation Mathématique Jacques Adamar, l'École d'ingénieurs La Rochelle et les centres de physique théorique. And it's my pleasure to introduce our first speaker, Paul Roux, who's going to tell us about combinatorial maps in critical loop models. Thank you.
Thank you for the introduction. So today I'm going to try to explain a recent work which we have done about loop models. So probably you don't even know what are loop models. So my first part would be to introduce loop models. So I will give you a short plan for the talk so that we know where we are going. Let me write down the title. All right, so my talk will roughly be divided into 3 parts. In the first part, I will try to explain what are loop models, defining them as lattice models. And the second part, I will try to give you a very, let's say, crash course on the CFT bootstrap. And the goal of this second part is to motivate and explain my last part, which is the main topic of this talk and the title of the talk, which is the relation between the CFT bootstrap of loop models and combinatorial maps. In this part, I will define first what I call combinatorial maps, and then relate them to the solution of the loop models. All right, so let's get going with the first part. So what are loop models? Loop models are statistical models. Defined on, so the version I study are defined on the two-dimensional models, two-dimensional lattices. And there is a great variety of models we call loop models, which are all slightly different, but which have universal properties, which are the properties which I'm interested in. So I take a 2D lattice, and I call a loop model on this lattice the following thing. So to define a statistical model, we need 2 things. We need to define a space of configurations, which mathematicians would call the universe. So let's say for completeness, I will take what is called the ON loop model on the hexagonal lattice or the honeycomb lattice. So I take a honeycomb lattice, which is not always easy to draw. And what I call a loop configuration on this lattice is the following thing. Quite an obvious definition. Just take some edges, you color them, and each vertex has to be adjacent to an even number. So since there are 3 edges, it's necessarily 2 or 0 to an even number of colored edges. So this would be a valid loop. This is a valid loop. All right, so my configurations are all of the possible loop configurations on this hexagonal lattice, honeycomb lattice. So this is configurations of loops. And then the second ingredient you need to define a statistical model is a probability law, of course. Yep.
It's fully packed. Like
No, there can be empty vertices. So
Actually.
here, for instance, I have an empty vertex.
okay.
I can have empty edges, of course. I always have empty edges.
There cannot be intersection.
And the loops, I didn't precise, of course, the loops are non-intersecting.
Okay.
Non-intersecting and non-self-intersecting as well. These are my configurations, and then I need to give you a probability law to define a statistical model. And the probability law is the following. The probability of a certain loop configurations L, loop configuration L, is just proportional to K, a certain constant K to the number of edges in these configurations, times N to the number of loops. So in the particular configuration I draw here, there are 2 loops, and there are 1, 2, 3, 4, 5, 6, plus 5 and 6 plus 10, so there are 16 edges in this particular example. So this has weight K to the 16, N squared. And I say proportional because there is, of course, for this to be a probability, you need to have a proper normalization. All right, so this defines for me a certain statistical models, a certain statistical model, and when you have a statistical model and you're doing 2D statistics, well, you're doing statistical mechanics, you have to wonder what is the phase diagram of this model. In this case, the answer is a bit subtle, but I will just sketch roughly what happens. So the answer is the following. The parameter n actually is related to a global ON symmetry of the model, which is completely not obvious in the presentation I gave of the model, but which happens to exist. So there is a certain ON symmetry. And since we have an ON symmetry, the parameter n is a symmetry parameter, so it doesn't flow under RG. And does not flow under RG. And so to study the phase diagram, we should just fix some value of n, fix n, and vary k, and see what happens. So at very low k, what happens is that configurations with many edges are very disfavored. So at very low k, we have very dilute and very small loops.
Isn't and the same as the ON? The end of the loops is the same as the
Right, so this is a very subtle point. N is in fact the same as the ON loop model. Here, N is just a real parameter, positive real, maybe if you really want this to be a probability. And there is a mathematically rigorous way to make sense of ON symmetry at non-integer n, which is called Deligne categories. But this would take me way too far from my purpose today. But indeed, n is the same n as here.
Should we think about the symmetry that we can exchange the loops and that's the symmetry?
No, so you should, in this presentation, there is absolutely no way to understand the symmetry.
Okay.
It's just that model is actually an expansion of a spin model where the spins are living on a sphere, and so there is an obvious ON symmetry in this presentation.
Okay, thanks.
Is it like you take the usual definition of the lattice model, like the generalization of the Ising models? So in terms of the spins on the
Exactly.
single on each single lattice point, and then you do some kind of strong coupling expansion into where you
That's right.
where you have these loops, And,
Exactly. Yeah, you
is
do
it, and then you see that in fact n appears precisely in this way. Or is
Exactly,
it-
exactly. You just do a high temperature expansion of the spin model where the spins now, instead of being just plus minus one like in the icing model or just vectors living on the sphere, if you do the
Okay.
expansion, you compute the integrals. It's a very elementary calculation and you end up with this probability law.
Thank you.
The problem in the spin formulation is that n is an integer, here n is just a real parameter.
Mhm.
Okay, so to connect the two, there is a mathematical framework called the link categories. But I don't want to speak about this. So I come back to my phase diagram. N doesn't flow under RG, so I just need to vary k. For low k, the model is very dilute. There are very small loops. And for high k, on the contrary, there are a lot of loops. The loops are very packed, and it turns out that there are loops of all possible sizes. Statistically, loops are dense.
If by low k you mean less than one.
I mean, k very small compared to 1. Yeah.
Okay.
And is there an interpretation of K in the sense of the usual, like lattice model, easing model?
Yeah, k is the temperature, so it's the
Okay.
the inverse temperature. K is proportional to beta.
So is it the equivalent of the two systems or only under some, in some regime of K?
You mean the spin model and the loop model?
Yeah,
Well, that's a
that's hard, okay.
that's a very tough question because it depends what you want to compute about each of these models. The partition functions are the same exactly for any k. But then if you start computing correlation functions, you may have multiplicities due to the spins and so on. So it's a very, very subtle question, which is why I didn't want to talk too much about the spin model. All right, so for very high temperature, the loops are very dense. And it turns out that there are loops of all sizes. And so in between the very low k and the very high k phases, we must have a certain transition at the value which we call kc for k critical. And it turns out that for n between 0 and 2, this transition is a second order phase transition. Second order phase transition at this value of the critical coupling. So, as someone doing CFT, I'm very happy with the second order phase transition because I'm used to the fact that when there is a second order phase transition, there is a close to the critical point, there is a correlation length which goes to infinity.
Sorry, for n equals 2 is precisely the DKT transition, no?
Exactly.
So it's infinite order.
So it's
infinite order because you don't break anything.
right indeed. So I should exclude the 2 maybe here, but it's still a continuous phase transition. So it's still a conformal, which is what was interesting for me. So the correlation length goes to infinity, and so the system acquires at Kc, the system acquires dilation and variance. Statistically, so if you look at the typical configuration of the system and you zoom on it, and you stay on a scale much larger than the lattice scale and much smaller than the total size of the system, you will not be able to tell a difference. So that's very usual in statistical mechanics. So there is a dilation in variance, and in fact, it is widely believed, although this is something extremely hard to prove mathematically in the generic case. It was proven for the icing model, I believe for the percolation model, and in each case it gave rise to a Childs medal. So for us, the fact that the symmetry is actually much larger than just dilation and variance and is enhanced through local conformal invariance. We kind of take it as an experimental fact or a widely accepted belief. And mathematically, this is something very hard to prove. But in any case,
So even the local conformal invariance is proved.
well, the local conformal invariance is the hardest
It's
thing we
harder,
can.
yeah, it's harder than global.
Yeah,
I see. So that has been.
local. If you are locally conformally invariant, you are a fortiori globally conformally invariant.
Right.
The
So
local
for
as
the Eason model, local has been
proven.
established.
Yeah.
But local, you mean the old Virasoro, or you just mean a special conformal? What do you mean by local conformal?
I mean that if you do any of the dilation, translation, or special conformal transformations, you will not be able to tell the difference.
So-
But I just mean that. Okay, so local
Just
conformal.
because in 2D you can have the old Virasoro symmetry, and then this is usually called local conformal invariance.
Yeah, exactly. So I mean much more than that. I mean that if you do any conformal transformation of the plane, so any holomorphic mapping of the plane to itself, and you take a configuration on the left plane and do the transformation and look at the configuration on the right plane, you will not be able to tell the difference
Okay.
statistically.
Mhm.
All right, so these models have a very large symmetry, which is local conformal invariance, large symmetry. And so as a field theorist, I'm very happy because if I have a very large symmetry, I have a very constrained theory and I have a chance of trying to solve it exactly. So exact solvability. Right, so then I should explain what I mean by exact solvability. I have a model. I cannot possibly ask to answer any question you could ever come up with about this model. I have to tell you, here is the set of questions I want to answer. And so this, in the case of loop models, the question we want to answer are of the following type. Say what is the probability of the following configuration where we have a certain lattice and we mark a given number of points. And we ask that maybe there is a loop, the probability that there is a loop going through all of the 4 points. Oops. This is a valid probabilistic question, which I claim we can answer with the CFT. Or another example would be the probability that given 4 points, a loop goes through these 2 points and another loop goes through these 2 points. All sorts of observables of this type. So this is how my combinatorial maps will later come up. Combinatorial maps are just the formalization of all of the possible connectivities we can draw between these points. All right. I should mention at this point that these models are also very much studied in the mathematical community by probabilists. For these people, these models are known under the name of CLE kappa for conformal loop ensemble, and the parameter kappa is related to n. And some very recent results by Shin-Sun et al. Have computed some of these probabilities. In particular, the formula for the 3-point function, so the probability that 3 points at given positions z1, z2, z3 lie in the same loop. This is now a theorem. It's exactly computed. There is a formula for it. It's the exact formula. And exact formula and proven. So we cannot possibly beat that with the bootstrap, but the appeal of the bootstrap is to be able to treat generic correlation functions instead of focusing on a single example. So we drop rigorousness and we gain generality.
The formula assumes global global environment.
So this formula is an exact formula for the CLE kappa model, which is a model directly defining the continuum, which does have local conformal invariance by definition. And then what is not proven is that this model is the continuum limit of the lattice model.
Okay, thank you.
All right, so now I turn to my second part. I hope I have given enough intuition about the lattice model to get you motivated to learn a bit about CFT bootstrap, which is what I do now. The idea being that the CFT bootstrap is the right formalism as physicists to try to compute these correlation functions there. So I will just forget everything about loop models for maybe 10 minutes, 15 minutes, and try to explain what's the formalism of the CFT bootstrap. So maybe first I should explain the word bootstrap. Bootstrap comes from the expression to pull oneself up by his own bootstrap, and the idea is just to make to have a self-consistent approach. So we make a bunch of assumptions, and then we check that these assumptions are consistent together. And just from these very self-related constraints, we're able to say a lot about the theory. So the bootstrap is an algebraic approach to field theory. Its main appeal, and the reason why it's been very popular lately, is that it's non-perturbative. There are not so many examples in field theory where you can do non-perturbative things. And I should say that different people do different things with the bootstrap. In the particular community I'm in, we're interested in 2D bootstrap, which is quite different, technically speaking, from the higher D bootstrap, which people here like Shavarishkov do. And the difference is that they use the bootstrap, you may know that they use the bootstrap for constraining parameters, reducing the region in which parameters are allowed to live. We use the bootstrap to guess exact results. The difference being that in 2D we have a much larger symmetry, and so things are much more constrained. All right, so what is the framework I've been advertising for now 5 minutes? It's the following. So it's an algebraic approach, so it's not constructive. We just assume that we have a certain structure, we have a certain number of assumptions, and then we check that these assumptions are self-consistent. Now we need to tell you what are these assumptions I'm speaking about. The first one is that there exists a space of states. I'd not call it a Hilbert space, simply because the scalar product which is defined on it is not necessarily definite positive. So let me think of a Hilbert space, but not really Hilbert, not a positive definite scalar product. And so the assumption that the theory is locally conformally invariant is translated in the fact that the conformal algebra, let me give a name to the space of states. I will call it purely S, or maybe just a regular S. It will be easier to write. So there exists a space of states S, and the conformal algebra, which some of you probably know is the sum of two copies of the Virasoro algebra, which we denote Vir and Vir bar, acts on S, acts linearly on S. So that's our first assumption. We have a certain linear space which contains all of the states of the theory, and the symmetry algebra acts on the space. So as is usual, when we have an algebra acting on a space linearly, we can decompose the space. We can decompose S into irreducible representations of the algebra. There's a slight oversimplification in this sentence because the conformal algebra is not semi-simple, so we cannot necessarily reduce any representation of this algebra into irreducible representations, but I will just ignore this technical detail and write S equals sum of certain modules of the algebra, which I will denote Vi. So these are irreducible representations. Irreducible representations of, let me give a name to this algebra, VR plus VR bar, we'll call it C. So for the conformal algebra with central charge C, if you don't know what a central charge is, it's not a big deal. Just take this as a notation. So that's our space of states. Then the second ingredient we need, of course, since we are doing field theory, we need the notion of correlation function. So we assume that there exists correlation functions. Which are maps, I should say multilinear maps that to a certain number of states, V1, Vn, map to a certain function of Z1, Zn. Right, so to n states V1 to Vn, I can associate a correlation function, which is a function that depends on n complex variables, which can live on the plane or maybe the sphere or a torus or a two torus or any Riemann surface, really. And that's what I call a correlation function. Now I need to explain how the conformal symmetry translates as a condition on correlation functions. And the condition is the following. Conformal, let's say, conformal symmetry. It imposes that the correlation function of any V1, Vn, where Vi lives in a certain representation Vi. So one of the representations here is determined in a known way, which I will not explicit because it's a bit technical to write. But just think in a known way, which is well-defined and not so hard to write, from the correlation function where Vi is replaced by the highest weight, and we'll explain in a second what is the highest weight in Vi. So said otherwise, if you know the correlation functions of all of the highest weights in this space, then you know all of the correlation functions of the theory. All correlations are determined from those of highest weight. What's the highest weight? The representations here are irreducible representations, and you can study the representations of the conformal algebra, and then you will see that all representations are highest weight representations, exactly as happens for SL2. All of you probably know the representations of SL2. You know that the representations of SL2 have a certain highest weight, and then by acting with SL2 ladder operators, you can generate all of the representations, all of the representation, I mean. And the same is true for the Virasoro algebra. So conformal symmetry is very important. It allows to reduce the problem of computing all of the correlation functions to computing correlation functions of highest weight, which we call in CFT primary fields. So this is just a definition. Right, so we have most of the ingredients for the bootstrap. We have the space of states. We have correlation functions depending on the state on the space of states. And the last ingredient we need is something called the OPE, which somehow expresses the locality of the theory, which tells you that if you take two fields close together in a correlation function, then you can just decompose this product of two fields coming close together over the space of states. So the last ingredient is OPE, and OPE is the following. In any correlation function, you can replace V1 of Z1 times V2 of Z2 by a certain sum of Vk of Z2, sum over K, and you have coefficients in this decomposition, which are called OPE coefficients, which I denote CK1, 2. All right. So that's the three ingredients we need for the bootstrap. That's quite minimal, but in fact, that's enough to say a lot about this theory. And I should say that for the OPE, so I have two different conditions. I have an OPE, and then I have some symmetry conditions on the correlation functions. And for the OPE to be compatible with the symmetry conditions I have imposed on the correlation function, these coefficients CK1, 2 of Z1, Z2. So for the OPE to be compatible with conformal symmetry, with conformal symmetry of correlations, CK1, 2 of Z1, Z2 have to be determined from the coefficients of primaries. So what I mean by this is that I can determine any correlation of descendants in terms of a correlation of primaries. This is what I stated here. And so now if I insert an OPs in a correlation function such an OPE, I will get some coefficients of primaries when Vk here is a primary, and I will also get some coefficients for its descendants. And for the two conditions to be compatible, the coefficients CK1, 2 are very constrained. In particular, you can just determine CK1, 2 for descendant fields in terms of the CK1, 2 for the primary fields. Okay, so already we have three rather minimal assumptions, and we see that we have a lot of structure. We know that products of fields expand in a very constrained way, but there is a lot more we can constrain just from these assumptions. So the last part of this rather formal bootstrap part is bootstrap equations. So starting from these three assumptions, how do we constrain the model? Okay, maybe just one thing I forgot to say is that using OPs, endpoint correlations computing endpoint correlation can just be reduced to computing 3-point correlations. Can be reduced to 3-point correlations. So our very hard task of computing any correlation functions of n fields just reduces to computing correlation functions of 2 and 3 fields, and this isn't completely obvious, but the 2 and 3-point functions, 2 and 3-point functions are fixed by conformal symmetry. Up to a constant. Right, so I hope you are still with me. We have to compute all correlation functions. Because of OPs, we can reduce this problem to computing 2 and 3-point functions. These are very constrained by conformal symmetry. They are just determined up to a constant, and so our whole problem is to compute this constant. And now I should explain how do we get constraints on this constant. And this constant, I should say, is related to the OP coefficients. You can quickly see that the OP coefficient is related to the 3-point constant, to the 3-point function. Right, so my last ingredient, as I was saying, are bootstrap equations. And there are two main bootstrap equations which are studied and used, which are, I will say the word and then explain what it means. Crossing symmetry of 4-point functions and let's say one crossing symmetry of 4-point functions and two modular of sphere 4-point functions and modular covariance of torus 1-point functions. So what do I mean by this? I will first explain the first point. Let's consider a certain 4-point function, p1 of z1, p2 of z2, p3, p4. I can draw it like this, p1, p2, p3, p4, 1, 2, 1, 2, 3, 4. Now I can use my OP and I could decide to OP 1 with 2, which I will represent graphically like this. So I will get a certain coefficient CK12 here with a certain field VK coming out of the OP. This is not a Feynman diagram, this is just a symbolic notation for performing the OP. And then I could also OP 3 with 4. And so this would be a certain decomposition of my 4-point function. So this graph, what this means is that I have written this 4-point function as a certain sum, CK12, CK34, times a certain dependence on the position, which I will call just GK of Z1 to Z4. And I should stress that this function here is completely determined because we said that the CK12 are completely determined from or maybe I didn't say it explicitly, but it is true that the CK12 had to be determined from the coefs of the primaries, and in particular, there, the I dependence is fixed, it's known. All right, so in our OPE, we know exactly how the coefficients depend on Z1, Z2. So when I do the suspension here, I do the OP of this one with this one and this one with this one. I know exactly how everything depends on Z1, Z2. It may be a very complicated dependence, but it is known. It is something which doesn't depend on the theory I'm looking at. This is just something completely universal. And this is what I call GK of Z1, Z4. And this function here, I consider to be known, and it is called the conformal block. I say I consider it to be known because it is not easy to prove that this is a convergence. So this will be a series in Z, and it is not so easy to prove that it is convergent. It is not so easy to find efficient numerical methods for it. But let's say, even though this is not stuff that is easy to prove, we consider it to be more or less known as physicists. So this is a known function. Right, so this is the first expansion I could decide to write for my four-point function, but I could have very well decided to first do the OP of 2 with 3, get a certain field VK here.
Just so a question.
Yeah.
So usually, like in, for example, in minimal models, these blocks, they satisfy some differential equation, and you just kind of compute you compute them but
Indeed.
in these loop models, like do you also have some kind of BP?
No, so for very specific blocks we do, but okay, the reason why there are I don't know how much technical I can get on this, but the reason why you have BPZ equations on the blocks in minimal models is because the fields are degenerate. So this means the representations which appear here are not Verma modules, but instead are quotiented modules. And this quotient gives a differential equation for the block. For most of the blocks which appear in loop models, these are actually Verma modules.
So the only way you actually compute these blocks is literally by just looking at the representation theory and.
So that's the most naive thing you can do, and it's very inefficient. Sadly, we cannot do this numerically. So there is a method called Zamolodchikov recursion,
Okay.
which is a recursion scheme for these functions.
Starting from what though?
Starting, so it's a recursion in the conformal dimension.
Yeah. Okay.
So there are two. There's a recursion in the central charge and one in the conformal
But
dimension.
these are for the global blocks, no? You can also find.
No, there is a Zamolodchikov recursion for the local blocks.
Okay. Thanks.
And so this recursion is not proven to work. It is not proven to converge. It is not proven to be.
What I know of this Zamolodchikov recursion relation is that usually, so you can use it, for example, to compute the global blocks starting from the Casimir equation. Then you have some initial condition, for example, large delta, where delta is the conformal dimension,
Yeah.
and then you write some dispersion relation. In this case, like what is the equivalent of the Casimir equation for the local blocks?
So we're talking about Grasson blocks, right?
Yes.
Yeah.
Okay, Grasson blocks.
Yeah.
These are very.
So what is the initial condition that you start with?
So this is something which I would like to understand better, but I don't have a good answer to this question. The large delta in the old paper by Zamolodchikov, which is very hard to read in my opinion, there is an argument for what is the large delta limit of the block. And this is how he finds the prefactor of the block. So the structure of the relation itself, of the recursion itself, is fixed by the poles of the block.
Yes.
This you can figure out reasonably easily.
Yeah.
And then you have to figure out what is the prefactor, which is something geometric, which comes from the large delta limit of the block. And this, to me, is a bit of black magic. I don't understand where.
You don't have like a Casimir equation.
So if I can say also for blocks in higher dimensions, you can use the whole structure to just
No,
get
but
there, and it should be also faster.
I agree, but what I'm asking is, so when you use this recursion relation, for example, in higher dimension,
Yeah.
for the global blocks, like you have an initial, so the initial condition, this prefactor is a solution of the Casimir equation at large delta. Now, of course, you also have a Casimir equation here, but it's for the global blocks, not for the local ones.
Yeah.
Like for the local ones, I don't know, there might be something else, but I don't know what you can use.
I'm not sure. So there is an argument where the four-pointed sphere is mapped to a pillow geometry. And then in this pillow geometry, they claim that the prefactor is easier to figure out, but I don't understand their argument.
Okay.
You can say you're worried about the boundary condition.
Yeah, it's just
Okay,
the
the
initial
structure.
condition of
Okay,
the.
I see.
Yeah. And if you say I've looked for a reference for this for a long time, and it's really hard to find. People just use these formulas.
I can imagine. No, I was just asking how you actually compute.
No, that's a very good question, very relevant. But
Okay, that's fine.
But will you need them in your style? Will you need to compute actually blocks or?
well, when you want to do actual computations with this, you do need to compute blocks numerically.
So also for the loop models and so on?
Sure. So we do a lot of stuff numerically to guess exact formulas numerically, and so we need to have the blocks.
Okay.
But I will come to this in a second. So the way we constrain these coefficients here is that we can choose to do this expansion, or we can also choose to do this expansion. And so this is a different decomposition. So sum over k, ck23, ck14 times a new block. So this I will call an S-channel block because it looks like an S-channel Feynman diagram. It's a T-channel block. Or I could do the last channel, which is 1 with 4 and 2 with 3. And whatever I choose to do, it should give the same result for the four-point function. So I can actually just equate these two sides of the equation. And now I have a linear system of equations. Go back to the left. I'm a bit late.
You got many tests, so you can take 5.
I can take 5 more minutes. Okay, so I have a linear equation, sum of CCG equals sum of CCG. We write this very symbolically. And now if I evaluate this equation for many values of the zi's, I get a linear system of equations on the coefficients c times c. And so if I solve this system, I can, in principle, find the coefficients c times c. Linear system. Solve numerically, or maybe analytically if we can. Get c times c. Now there is a slight complication, which is that if in the space of states there are several operators which have the same conformal dimension, so which live in the same representation but different copies of this representation, then the blocks here, they only know about the conformal dimension, so the weight of the highest weight. And so in fact, if I solve this system, instead of getting CC, I will get a certain sum of CC, where the sum is over all of these fields which have the same conformal dimension, but which are different fields. And so if I could get the C times C, then I could easily just see how these factors and get the C themselves and be done, have solved my theory.
Sorry, just another technical question.
Yeah.
So in when you solve this equation, so do you know actually the dimensions or not?
Well, that's precisely the point which I'm getting at.
Okay.
In a minute.
But so do you know the fusion rules, for example, or no? In this case,
No. So the whole point is to.
So you solve both for the dimensions and for the p coefficients.
Oh, okay, right. So I misunderstood what you meant by dimension. We know the dimensions, right? This is something I should mention. But I just want to finish my general bootstrap, and then
absolutely
I will go back to loop models and everything. I hope will become clear. So if we solve this numerically, we get these sum of CC from which we can hope to get back to the C themselves. but this is not a trivial step, fortunately. All right, and another equation you can write is that if we write the one-point function on the torus, so with a certain modulus tau, we know how this should transform under a modular transformation of the torus. And this is simply -1 to the some coefficient which is determined by V1, some powers of tau and tau bar, times the same correlation function on the torus of parameter tau. And so again, if we expand this into different blocks and solve the linear system, then this time we will get almost the same kind of constraints, except now if you do this, so I'm not being very explicit, but I'm just telling you the result, you will get constraints, get sum of C K11. Again, the sum is over all of the operators which have the same conformal dimension. All right, so that's for my general bootstrap part. It took a bit longer than I hoped for. And now I can come back to my loop models. And at this point, you might be either asleep or worried that it's not going to be easy to make the link between the lattice model and the bootstrap formalism, which is algebraic and very abstract. Yeah.
Can I ask
A question on that.
Yeah.
On the modular bootstrap of the one-point function there, like to your space-time dependence, does it happen anything when you do the modular transformation?
There is no spatial independence. This is a translation invariant.
Okay.
So one-point function has no dependence on Z,
Okay.
just because of translation invariance.
Okay.
All right, so how to make the link between lattice and bootstrap? Well, this is way too complicated of a question for me to give an answer in less than 10 minutes. So I'll just tell you how it's done in words. So you can either compute a torus partition function. You can do some numerical transformatrix computations, numerical transformatrix, or do some lattice diagram algebras. So these are just words for the people who have heard about them. I will not explain what they are. But in any case, the result of these techniques is that we know exactly, we know exactly the spectrum. So we know all of the conformal dimensions. We know exactly what representations of the conformal algebra comes with them.
Sorry, you don't ask in the sense that you know how many of the degeneracies at each delta?
No, so that's the one certainty we don't know about. We know S.
So you basically know the partition function.
Up to multiplicities.
Yeah, so that probably means you know the partition function. That's
We know the
partition function.
well, not even because the partition function knows about the multiplicities. But what
Not partition function with
then if I
it
take
doesn't really know the you don't I see. You don't know the multiplicity.
we don't know the multiplicity. So in particular examples, say the ON model which I introduced in the beginning, we don't know the partition function exactly, but then the notion of multiplicity which appears in the partition function is not a good notion of multiplicity because it is not an integer multiplicity, so it makes absolutely no sense in this algebraic framework. And the question of understanding these multiplicities is, in my opinion, the ingredient that we lack in order to get a full solution to these models.
Sorry, I didn't get this, but if you know the torus partition function, this is going to tell you also the multiplicities.
Yes, so we know the torus partition functions in particular models, but the multiplicities are not universal. They depend on what model exactly we look at, and they are not a good notion of multiplicity because they are not integer coefficients.
The torus partition function for the loop model.
Yeah.
which is different from the CFT interpretation.
Exactly.
That's your plan. Okay.
Exactly. So this, in the loop model, I can compute the critical limit of the lattice partition function. I will get something like this. Some character of an ON representation times the character of Vier's row algebra, of conformal algebra. And the problem is that these characters here, when you take a, so this would be dependent on a ON element G, and when you take G equals the identity, these are not integers for generic N. So that's bad, and we don't really know how to solve this problem basically. All right, so we did a very
I mean, it makes sense because of course, especially because ON for generic N is not like a group, it's
Obviously,
like
yeah.
a category.
Yeah.
So it makes sense.
It makes sense, but then it makes complete sense as an algebraic fact on the lattice model. But then to make sense of it as a multiplicity in the bootstrap approach,
Yeah.
it doesn't make sense.
Yeah.
So connecting these two is something we don't know how to do.
Yes, also the CFT interpretation is not, it's not easy, I mean, it's not direct. Right, that's the issue also.
Yeah, and also, so the CFT, we expect it to be very universal. We expect it to describe a whole host of lattice models independently of what exactly the lattice model is because of universality. But these multiplicities are very dependent on what type exactly of lattice model you look at.
But we have to have from these three methods, you can get numerically the spectrum.
No, we get it analytically. Exactly. Yeah.
Okay, and you get it for generic N.
Well, analytically here and here, and numerically here for generic N.
Okay, thank you.
So that's a lot we know about the CFT. And the lot that we don't know is multiplicity, basically. At least that's my opinion on it. All right, so now I have less than 10 minutes left to speak about combinatorial maths, which was the initial title of the talk, so I better get going. Combinatorial maths. So what happens if we take this S that we know, plug it into the bootstrap equations and try to solve? First, let's look at what happens with crossing symmetry. Crossing 4-point equations. Well, the situation is the following. It was a result found in a paper which was published around 2 years ago by École, Ribot, and Staller. The dimension of the space of solutions. So these are linear equations. So their space of solution is a linear space, and it has dimension equals to the number of combinatorial maps. I didn't explain what are combinatorial maps, and I'm coming to this right now. So I told you in the beginning, and I just erased it, that the probabilities we are interested in are probabilities of the type of the following type. Take a given number of points. I took 4 points because I'm now looking at 4-point functions, and at each point, I can ask that a certain configuration of loops goes through. So let's say this one. And the way we think about this is, and of course, the rest of the model has loops everywhere, randomly distributed of all types of sizes and shapes. And the way we think about this is that this probability can just be represented by a certain combinatorial map. So a combinatorial map is the data of a certain number of marked points, which we call punctures. And at each point, there can be two things. Either there can be a certain number of loop strands outgoing. Let's say in this particular example, I have 2 loop strands outgoing at each point. Right, so that's the first possibility. Or a second possibility, which I didn't really talk about, is that it could be that there are points around which there are no loops going, but we change a bit the problem and ask to compute the probabilities where we change the weight of loops which go around these points. It's not easy to explain why, it's a bit of a technical reason, but just to admit that we have these two types of points. And the mapping between the lattice and the CFC model teaches us that such an insertion here corresponds to what we call a diagonal field. And the diagonal field is simply a field in the spectrum, in the space of states, which has the same left and right conformal dimensions. So it has the same highest weight for the Vira-0 and for the Vira-0 bar algebras. And such a field like this one, we call it a non-diagonal field. And generically, it has different left and right conformal dimensions. And we are able to tell, given the number of legs and the spin of this operator, here is the corresponding state in the space of states. So this I denote VP, and this I denote VRS. And so this leads me to my last point, which is what are combinatorial maps? A combinatorial map is simply the data of all the different ways we have to connect a certain configuration of outgoing legs at each point. So if I take this particular example where each point has two legs outgoing, or maybe let's do even a simpler example where each point has one leg outgoing. You can connect them in various ways, and precisely there are three ways to connect them. Here's one. Here's two. And here's the third. Track. So three maps with 4 times 1 leg. And in general, there is a formula. There exists a formula for the number of maps with 4 points and ni legs at each point. And the very interesting fact is that this formula for the number of maps, so this number of maps with a given number of legs exactly matches the dimension of the space of solutions of the corresponding bootstrap equation, the corresponding crossing symmetry equation. And the same is true on the torus. We can also define combinatorial maps on the torus. We can count them, and if we solve the bootstrap equations on the torus, it is expected and verified in some cases that the dimension of the space of solutions of the modular invariance on the torus is going to be exactly the number of combinatorial maps.
But I thought you said one point function has no space dependence, so no space-time dependence on the.
Right. So the way we get equations here is by evaluating it for many values of tau.
Ah, okay.
So now we can, if we evaluate it for every possible value of tau, we get an infinite linear system we can solve.
No, I mean this means your one point function has to be put on the point, and then you think about combinatorial maps. Or...
Okay, so what are maps on the torus? I can try to give a few examples. So let's say I take an insertion with 4 legs.
Yeah. Ah, okay.
I didn't say one thing important about these combinatorial maps because I'm really tight on time, which is that the legs coming out of the point are ordered cyclically.
I see.
So, for instance, if I had 3 points or 4 points, these two maps, this is different from this one. Because the cyclic order is different. So that's just a definition about combinatorial maps. We have to say exactly what we want to compute. And this is exactly what we want to count as different. And on the torus, so I draw the torus as a rectangle, this then identify with this and this with this. And then if I have, let's say, 4 legs outgoing, well, I have 2 possible combinatorial maps, which are the following. Either we have this, or we could have this. So these are 2 inequivalent maps, because here the leg 1 is connected with 3 and 2 with 4, and this here 1 is connected with 2 and 3 with 4. And you cannot make these 2 equivalent by a cyclic reordering. Right, and the point which I don't really have time for is that
You can take some.
I can take 5 minutes.
Yeah, you got many questions.
Okay, perfect. So this will just give me enough time to come to my last point, which is that we can, first thing I have to say is that we can also count maps with 1 insertion point on the torus. We can find it's a reasonably easy combinatorial exercise. Here's my eraser. It is actually the case that the number of maps on the torus, the number of 1-point maps in the torus, is equal to the number of 4-point maps on the sphere with so number of 4-point maps with let's say n legs on the torus. N has to be even, otherwise I cannot connect full of the legs. Is equal to the number of 4-point maps on the sphere with 1 insertion with n legs and 3 insertions without legs. Up to cyclic reordering of the 3 reordering of the 3 legless insertions. And now, if you are very cultured in CFT, you might know about a very weird relation in CFT, which is that 1-point functions, let's say in Liouville theory, for instance, but it is believed to be more universal than that. 1-point functions of operators on the torus are related up to a prefactor, which is not particularly interesting, to 4-point functions. So this is on a torus tau and with a central charge C. They are related up to a prefactor to the same 2 4-point functions where there is 1 field with a slightly different dimension and then 3 insertions, which I denote V0 1/2 tau, not tau, sorry, so on the sphere now. And the central charge is n. So you can map a 1-point function on a torus to a certain central charge C to a 4-point function on the sphere at a different central charge and with a slightly different conformal dimension for this operator. If you insert, so this is 3 times this field. If you insert 3 times these fields, and in our mapping between lattice and bootstrap, this field happens to be a field without leg insertions, just like in the mapping here. So it seems that the mapping of maps on the torus to maps on the sphere is very reminiscent of the mapping of 1-point correlations on the torus to 4-point functions on the sphere.
With more about this relation, like well on the space-time dependence, are you fixing this on the right-hand side? I mean,
Right, I should precise this, and then the answer is that I should evaluate, so this only depends on a certain cross ratio,
Mhm.
and there is a prescription for what the cross ratio X should be in terms of tau. I can make it more explicit, but
Okay, no, I see. Okay, maybe later.
maybe if you know about the norm Q. If you know about the norm Q, I don't know. The norm Q. So, no, okay.
So you are essentially evaluating this 4-point function on a particular configuration of points. Yes. And this particular configuration corresponds to a certain value of the cross ratios, which is also related to tau.
Yeah, I'm evaluating it as at a certain particular position of the 4-point.
Yeah.
Which is fixed by tau.
Okay, we appropriate.
And I can just say as a concluding remark that this relation is a bit mysterious, but it is related to a geometric correspondence between the torus quotiented by Z2, because this has a Z2 symmetry under flipping of the torus. So if you quotient the torus by Z2, then you get something which looks a lot like a 2 covering of a 4-pointed sphere. And this is how this relation is proven. So this relation is true in UV theory, and we expect some form of it to be verified in loop models, but we don't know exactly the right form. Right, and that's what I wanted to say. Maybe as a concluding remark, is that all of these nice bootstrap equations give a lot of constraints on the structure constant of the theory, so these coefficients CK12. And at this point, we have a lot of exact results for the 4-point constants, so the sum of CT. We have a lot of exact results for these, so closed form analytic formulas guessed from the numerical bootstrap. And currently we are trying to get the same kind of results for the sum over C. And from this, hopefully, we could start to try to factorize this into actual results for the C's and Th's. If we were able to do so, then the theory would be fully solved. Right, that's the best.
Thank you very much. Maybe let me first ask if on Zoom there are questions. Otherwise, people in the audience, some more questions. Or we can continue.
We can talk.
Yeah, let's continue perhaps
After, okay.
yeah. But thank you again. Thank you.
The year is fourth.
Yes, I guess. Maybe I can also do that.